All right, so now let's take a look at ionic bonding. So again, ionic bonding results from elements that have very dissimilar electronegativities. So the example that we just looked at was magnesium oxide, and those were quite a bit over 2 apart, whereas silicon carbide, which was much less. A classic example of ionic bonding is sodium chloride. We also have calcium fluoride and cesium chloride. So all of those, as you kind of see, are from very different parts of the periodic table. Over here, way to the left. Over here, way to the right. So very electropositive, very electronegative. So basically, low number, high number, right? That's what we're looking for here. And so these are predominant bonding in ceramics. So ceramics have a lot of ionic bonding, and we're looking at very dissimilar materials. So you notice that chlorine has a very high number, oxygen, fluorine, all of those paired with more electropositive things here on the left side of the periodic table are going to give us predominantly ionic materials. So as you may be aware from basic chemistry classes, ionic bonding is the result of bonding between a positive and negative ions. Because those elements that we saw in the previous slide here, these really want to give up electrons to become positive ions. These really want to gain electrons to become negative. So what happens is each of those elements does so. They give and they have an electron transfer. So sodium gives up an electron to go to chlorine. So that leaves us with 2 ions, positive sodium here or over here, and negative chlorine over here. And that's a result of that large difference in electronegativity. So that's how ionic bonding happens, is there's large differences in electronegativity, which results in the formation of positive and negative ions, which then results as, so now we have a positive ion, so this is net positive, this is net negative, and so these 2 ions are going to be strongly attracted to one another through that charge effect. So in general, we think of this as a metal, which tend to want to give up or donate electrons, and then the non-metal, which tends to want to accept electrons. So that's the general kind of thing that people think about is metal, non-metal for ionic bonding. And so that would be something like magnesium, which is a metal, and oxygen, which is a non-metal. Those 2 together have dissimilar electronegativities, like we saw in the previous exercise, and so those will want to exchange. And so in this case, magnesium, if we look at the electronic configuration, has an extra 2 electrons in the 3 shell. So instead of trying to add a bunch to fill up the N=3 shell, it's going to get rid of those 2. And oxygen has 6 valence electrons in the N=2 shell, and it needs 2 more in this N2p to become filled. So it's going to take those electrons from magnesium, and then they will both have completely filled outer shells like the noble gases or inert gases around them. So neon here is what we see, and then also the same thing, neon for oxygen. So after the formation of ions, the configurations are like we see here. And so that's neon for both. So if we go back to the bond energy diagram for an ionic structure, again, we have that attractive force here negative and the repulsive force here positive, and the net energy is the red curve, where the energy well, the lowest point here on the attractive force side, the negative force, that is the equilibrium bond spacing, so interatomic spacing. So that's the spacing, that's the R value between those positive and negative ions, and the energy will be the depth of that well, so the E0 value here. And so we term the attractive force Coulombic because it deals with charge. in this case. So if you hear Coulombic, think of charge. So that's the charge difference making for attractive force or energy. So that Coulombic force, the attractive force, is a function of the charge and the radius, so how big things are. So the greater the charge is, so if we have +1 and -1, that's going to give us a certain level of force. But then if we have +4 and -4, that's going to be a much stronger force because of the term here with z, the charge here for 1 and 2, and then E is the charge of electron. And then it's inversely proportional to the radius. So the radius r here is down here, and that's the separation distance between ions. So the smaller that separation distance, since it's on the denominator, the larger the force gets, and it's even amplified by the square here. And so the other terms, the epsilon here, epsilon naught is the electronic permittivity. So this is a constant given here. The charge of an electron is also a constant. It's in coulombs. And so then the unit charges are Z1 and Z2. So for +1 and -1, those are equal to 1. So we can calculate what the force is on these ions by the charge and the radius. The repulsive force, like I mentioned before, this is from the overlap of the electron clouds. And so that only occurs when they get really, really close together. And so we can model that repulsive force by having a constant K and then over R, so the radius, to some exponential. And in this case, it can go anywhere from 2 to 12. So it's drastically, the force drastically drops off as these ions get further and further apart. The closer they are, it goes up very quickly. And so this can be anywhere from 2 to 12. So it's going to depend on a lot of things there. So we just want to give a general idea of what these forces look like. So we have, right now, we've talked about the Coulombic or attractive and then the repulsive force. So those are the two terms we talked about in the bond energy, bond force. However, ionic bonding actually has an additional energy term, and that is the result of having to form ions from the neutral atoms. So sodium is an element. We have to remove an electron from it, and that requires energy. It actually requires 5 electron volts. Chlorine has to remove an electron. We have to add an electron to chlorine to get the ion formation. And so that recovers or liberates energy. And so the combination of those is required in the overall energy scheme. And so that is an additional term that we have to account for. And so that's, so basically if we put all those things together, and again, don't worry too much about how we got the equation, but if we sum all 3 of those components for energy, we get the Coulombic term, we get the repulsive term, and then we have this e to the sub I, which is that ionization energy. So that third term is a result of that. And in this case, the book is giving the value for this repulsive term N as around 8, but again, it can change. All right, so this is kind of what that results. So this is the energy diagram for an ionic bond. So because we have that additional energy term, the net energy as the ions get further and further apart, we see that it actually goes slightly positive here. So it goes slightly above the axis. And this term, which is labeled UI, is the same thing as the EI. It just is that ionization term. So that's the only difference between the bond energy diagram for ionic bonding compared to generic bonding energy diagrams.